In the previous unit, we talked about networks and their representation through graphs, nodes, links that represent the connection between the different data points. But we didn't talk about music and how music fits in this in this picture. So in this unit, I will introduce you to a way of representing musical spaces using networks. And when I talk about musical spaces, I talk about melodies or harmonies or rhythms, timbres, orchestrations, so the arrangements of the different instruments in a particular song, for instance, and how this can all be represented through network, and giving us this view of music through the complexity of the graphs. In what follows, we'll concentrate on the Western classical music tradition, but this approach is completely general. You can apply to any musical tradition, being Western or not, and one can see how there are some universality structures that emerge from the representation of these musical spaces through networks. The individual elements or units that we will use in defining these musical networks are actually the pitches, the individual notes that form the basis for this classical music tradition, and not only classical. Pitch is a perceptual representation of a sound through its frequency and timbre, and it's what we hear when we hear a note played by an instrument. In the Western classical music tradition, there are 12 pitches that are defined as that are tuned to a particular temperament that we call equal temperament. This is not very important in the following discussion, but it's something that you should keep in mind. There are musical traditions where there are more than 12 pitches, for instance, where the tuning is different, and it depends on the particular instruments or the particular genre or style of music. So with these 12 pitches, we can create all the possible melodies, all the possible harmonies, and so they provide us with an enormous space that we can explore by combining them. So in a way, one of the most famous novels by Jorge Luis Borges, The Library of Babel, he hypothesized a potentially infinite library where each book contains all possible combinations of the 26 characters of the alphabet. And so eventually, out of all these possible combinations, you might have a book that is Moby Dick, for instance, but or the Odyssey, but in this infinite number of combinatorial possibilities of letters arranged in all possible ways. And in a way, what I want to kind of push is the idea that we could do the same with the pitches of with the notes of our music, and basically construct all the possible spaces that connect notes with each other, or they can connect chords, so combination of notes with each other. So in the following, I will talk about mostly the concept of harmony space. That means all the ways that I can construct a vertical combination of pitches in chords. So, typical chords in the in any song, you have succession of chords that provide the backbone of the harmony, of the progressions of the song. And we need to start doing some kind of mathematical abstractions here. So as you can see in this slide, I can construct all the possible combination of these 12 pitches in this harmonic space by basically calculating all the combinatorial possibilities, excluding all pitch repetitions, all permutations within the same chord, so that I reduce this space to kind of a minimal dimension. And if I do this, I still can combine the 12 pitches in a large number of effective chords. So in this reduction, if I use 12 pitches, I can construct 4096 chords with different numbers of notes per chords. But if I extend this to a 24-note space, so a different temperament, a different tuning system for different cultures, musical cultures, these combinations become enormous. So in 24-note space, we go higher than 16 million possible chords. And if we look at the whole keyboard of a piano, as you have here in the slide, and we think about all the possible chords that we can combine notes with, then we get to an astronomically large number of 10 to the 26 different chords. So out of all this possible combination, what we want to do is we want to construct a geometrical model of this harmonic space. And remember that here, what we are looking for is how we can represent this harmonic space through a network representation, through nodes and chords and links. So in this approach here, we consider chords as ordered pitches, combination of pitches, that mathematically can be seen as vectors. So a vector of 3 components is, for instance, the first chord in this slide, in the left corner, is a C major chord, is a vector of 3 different pitches. On the other hand, since we are defining a vector space, we can associate to this vector space a concept of metric, of distance. How far are chords within the space, and if we can quantify the distance. And indeed we can. And it's actually relatively simple. We just generalize the Pythagoras theorem, is the Euclidean metric, that gives us a distance between chords. By doing this, we basically define our nodes of the network as the vectors, the chords, and we hypothesize links between chords based on their distance. So if I decide I want to see all the chords and the connection between chords that are distant, say 1 in the space of chords, then I will have a network representation that corresponds to this metric. In this slide, I'm showing you a very complex network of chords. This is a network that is obtained using the 24 pitch space. So it's larger, this larger pitch space that I was talking earlier. And I'm only connecting nodes that are distance 1 from each other in this metric space. And you see that the representation of this network becomes extremely complex and actually even artistically pleasing, if you wish. And we'll talk about what the different colors mean in this image in the next slides. So in order to make things easier and kind of follow more the relationship between all these geometrical elements, let's focus on a subset of chords of the 12 pitch space that are the chords made of 3 pitches, the triads. And what I'm showing in this slide are the networks that are formed building links at different distances. So the first one on the left is the network where I'm connected triads that are distance 1 through each other. That means that I can go from one chord to the next chord by changing only one note by a semitone. If I do a similar representation, but for a distance, say, square root of 2, like in the right top corner, then the topology of this network changes. Instead of having one single network, I have two networks that are separated. That means that the movement from one chord to another is constrained by this topology. And if I want to move by square root of 2 in this space, I can either stay on one network or in the other. And so on and so forth. I mean, the square root of 3 is also a bipartite. It's a kind of two different networks. One very small that contains chords that are very dissonant, and another one that contains all the chords that are more harmonious to our perception. So not only we have a representation of a space that we can navigate as composers, for instance, choosing paths through these networks, but we also have some sort of classification of different chord categories that emerges from this representation itself, so from the topology of this representation. So what I'm showing you here is some sort of a map of a space that we can navigate and that composers navigate when they write music that is based on these particular chords. So the classical chord progression of a rock song, for instance, might belong to one or more of one of these networks that I'm showing you here. And this kind of spatial representation or topological representation is very much linked to what we learned by talking with Professor Dmitry Timoshko about the geometry of chords, of chord spaces in one of the previous units. Now, this is not a composition, this is just a map. And so how do we do a composition starting from this mapping? Well, the composer here becomes the agent that takes from this deterministic representation of the pitch space the complexity of a work of art or a piece of music as an emergent property of these systems.